will be Ethernet switching. So I will let you know what are the points to focus on, because definitely there will be some questions on this one in the final exam. I'm sure already all of you know what Ethernet is. Ethernet is your means of communication to the outer world or to the internet. So every device or every computer needs to be connected through the Ethernet. Okay, so change the pen color. All right, so there is a concept here called Ethernet frames. The Ethernet is one of two LAN technologies. The other one is the wireless. So Ethernet is more into wired LAN, the Ethernet. Used today, with the other one being the wireless. And you know, the Ethernet usually have the RJ45 kind of cable to connect it, which is a twisted pair. However, that's the one that we are used to see, but there are other technologies, and you'll see that like each protocol and what is the technology associated to it. So Ethernet used wired. It could be twisted pairs. That's widely used one. Now we have fiber optics and coaxial cables. And I'm sure by now we all know that fiber optics is the fastest, yet the most expensive. Ethernet operates in the data link layer and the physical layer, so it falls in between. We'll see in the next slide the OSI layer system, and we'll see that the Ethernet combines both physical and data link layers. So in terms of protocols or technology, Ethernet falls in the family of the IEEE. Remember, IEEE is the one who, let's say, is the association that does let's say the regulatories regarding networking. So the protocols associated to the Ethernet are 802.2 and 802.3. Now, in fact, we'll find that this one is related to something called LLC, and this one is related to MAC. And we'll talk about each one of them separately. It comes in various speeds, 10 megabit per second, all the way to 100 gigabit per second. This is just an example, no need to memorize. So what you need to memorize in this one, Ethernet is wired. Could be a twisted pair, that's the widely used one. It connects both data link and physical layers. The protocols associated are 802.2 and 802.3. So this chart here shows the OSI model. And as I mentioned, 802.2, that is associated with LLC, and 802.3, that is associated to the MAC or MAC, Media Access Control. Both of them will create the Ethernet concept. Okay, so we have this layer system, it's a seven layer system. However, if you look at it, this data link layer here is divided into two parts. So we'll call it sublayers. So the data link sublayers consist of two parts. The first part is called LLC sublayer, and the other one is MAC sublayer. So the IEEE 802 is, let's say, that's the general term that's for all kind of networks, local area networks and metropolitan area networks. Ethernet falls under that category. So there are two sublayers in the data link, and they are the logical link control, and the other one is media access control. So from the name, logical link control is kind of related to softwares. So no hardware. So yeah, the IEEE 802.2, that is the LLC sublayer, is the logical link control sublayer. The main job is to communicate between upper layers and the data link layer. So between the networking software at the upper layers and the device hardware at the lower layer. So it's intermediate layer, like in here. So here, the oops. Okay, I think, okay, I need to go back to the pin mode. Yeah, so there you go. That's the job of the LLC. Now the MAC sublayer, it has a lot of variations, 3, 11, 15. They are all implemented in hardware and is responsible for the data encapsulation. If you remember, encapsulation means that you are putting headers and trailers to your original data package. So you put the data in capsules, encapsulation. So there you go. So let's not worry about the network layer here. It's the IP or the internet protocol, whatever. Now LLC sublayer, that's the main thing here. Okay, the color does not appear well. Yeah. So focus, LLC, the logical link control is 802.2. Now the MAC sublayer is all the family of 3, 11, and 15. So Ethernet, that's what we're gonna focus on, is the one with the 3. 11 is associated with wireless local area networks. The PAN is the personal area network. Let's not worry about those. All of our focus will be on this one. So various Ethernet standards for fast gigabit Ethernet, etc. Fiber optics and notice like it's kind of a connection between the physical and the data link. That is the MAC sublayer. So the MAC sublayer is responsible for the data encapsulation and accessing the media. Data encapsulation means that, so I have my data here. Remember, we have first TCP header, then IP header, and then we have this Ethernet header and trailer. So this is what we call encapsulation. This is my original data, and this is the whole set of encapsulation. So MAC sublayer is the one who will do the encapsulation here. It will add the header and trailers for the package. So it includes the following. An Ethernet frame, again, that's 8020.3. The Ethernet frame, this is the Ethernet internal structure of the Ethernet frame, Ethernet addressing. And here is a very key point here. We have IP addressing. Here we will have MAC addressing or media access control address. So the Ethernet frame includes both of the source and destination MAC address. And we'll talk a lot about this topic, MAC address. To deliver the Ethernet frame from one network interface card to the destination interface card through, let's say, they share the same local area network. And there is an Ethernet error detection. We'll see this whole thing now in a figure. The Ethernet frame includes a frame check sequence, trailer, and that is for error detection. Yeah, so if you were asked, what is the job of the frame check sequence? It is the error detection. The other job is accessing the media. So Ethernet has two parts, data encapsulation, some processing, and accessing the media. Again, referring to this one. So this part here, it has a lot of this one happens here, the data encapsulation part, and here is the accessing the media. Includes, okay. Sublayer includes the specifications for different Ethernet communication standards over various types of media, including copper and fiber. So remember, we have 802.3. We will have A for something, B for another thing. There will be AB, there will be probably C. And this figure kind of shows the idea. So in here, this whole thing is the Ethernet part. Now, if it's the letter U, that means that's a fast Ethernet. We don't have to memorize it, but to just tell you how to differentiate between different technologies. If it's Z, that's the gigabit Ethernet or fiber over fiber. AB, gigabit Ethernet over copper. AE, 10 gigabit Ethernet over fiber, so it's faster, and so on. So they all fall under the same family, but the variations, you start the alphabets like A, B, C, the letter U, for example. And yeah, this is how communication through the network happens. All right, so here's an important thing about the frame field of Ethernet. when a computer receives an Ethernet frame, as a part of some error checking, it checks the length of the Ethernet frame. So if the length is less than 64, it will discard it. And if it's larger than 1518, it will consider it large. So the range of size of the Ethernet frame between 64 to 1518. It's very important to memorize these numbers. So any frame which is less than, let's say the length is less than 64, it will consider it as a collision fragment or a runt frame, and automatically it will discard it by the receiving station. So if this computer here receives a frame and it was 50, it will discard it. It will not accept it. The other case, when the size is larger than 1518, it will consider it as a jumbo or a giant frame. So in that case, again, it will also discard. In both cases, the frame will be discarded. Now here just tells you how the frame looks like. So there is a preamble. Let's not worry about it. So there are 6 bytes for the destination MAC address, 6 bytes for the source, 2 bytes for type length, and here data, and this is the range of the, let's say, the size of data. And here we have the FCS, the let's say error detection technique, as mentioned here, the frame check sequence. All right, now we're going to talk about details about media access control address. So it's a 48-bit number, keep that in mind, and it's divided into 24 bits and bits. And by the way, 48 bits, that means it's 6 bytes. So this one here means that we have 3 bytes and 3 bytes. So this one usually is expressed in a hexadecimal number, hexadecimal digit. Now why 12? Because remember, each byte is represented by 2 hexadecimal digits. Remember, the byte is 8-bit number, and when you group each 4, we'll get any value between 0 to F. That's the hexadecimal number system. I'm sure you guys are aware of it. So points to memorize here. It's 48-bit number, which is equivalent to 6 bytes, and is divided into 12 hexadecimal digits. Now, all MAC addresses must be unique. Think about it like an IP address. It should be unique to the Ethernet device or the interface. Otherwise, there will be confusion. The message will not be delivered to the right address. So MAC address is a unique number. Now, to ensure this, all vendors basically is the manufacturers, must be registered with IEEE. There you go. So any company who wants to go into the Ethernet business or network devices before, let's say, manufacturing this, must get their permission from IEEE to get their unique number. Now, here's the thing about that number. Now, remember, it's a 48-bit number. I divided it into 24. So the first 24-bit or 3 bytes or 6 hexadecimal numbers, they are just unique for the manufacturers. So this is for the company ID, let's call it. And this is the device ID. So to ensure this, all vendors that sell Ethernet device must register with IEEE to obtain their unique 6 hexadecimal. Unique 6 hexadecimals mean unique 3 bytes. So 6 hex numbers means 3 bytes or 24 bits. Code called the organizationally unique identifier. So there you go. The first 24 bits or the first 3 bytes or the first 6 hexadecimal digits, they are the organizationally unique identifier. They are just unique for each company. Now the other values or the other bits, it's up to the company to decide their values. So when a vendor assigns a MAC address to a device or Ethernet, they must take into account it has the organization unique identifier as the first six hexadecimal digits, and the other ones that like the unique value for that particular device. So yeah, the Ethernet MAC address consists of 6 hexadecimal vendor OUI and 6 hexadecimal unique for the device. And there you go. This figure kind of tells the whole thing. So we have 24 bits or 6 hexadecimal digits or 3 bytes. That's for the organizationally unique identifier. And then the vendor assigned, which is the device, that's more related into the device. It has the same division, 6 and 3. Now, here is the thing. Sometimes two companies, they might have the same vendor assigned, but what makes them unique is the organization. So that's a key point here. Each organization have their own unique number. All right, so frame processing. So the MAC address is referred to a burnt-in address. So this address will be stored in the read-only memory of the device, in the ROM, on the network device. And it cannot be changed. So once the network interface card comes out of the manufacturer, it will have its own MAC address and it will never change. So MAC address is referred to be a burnt-in address because the address will be hard-coded in the ROM. Okay, so that's from the frame sequence before. So that's the destination address, source address, and here is the data encapsulated. So here is what's happening. When some computer sends a message, each computer will check the MAC address. So this is not address to me, shall ignore it. Not address to me, ignore it. This is mine, it will take it. So this is as simple as it goes. And we'll see the mechanism in a few slides. Now, transfer modes or sending modes, pretty much like the IP addressing. There is unicast, multicast, and broadcast. Now, in here, we're going to deal with each MAC address as a unique number, which it is. But this is going to be my, let's say, my destination or my source value. Pretty much like what we did in the IP addressing. Here, we're going to do a MAC addressing. So a unicast MAC address, it's a unique number. You see, it's just point-to-point transmission. You send from one device to the other device. So it's a unique address that is used when a frame is sent from a single transmitting device to a single destination device. So this is a point-to-point. And there you go. So this is my source, and here's my source MAC address. And then here, this is my destination MAC address. So when it comes to the frame sequence, here's the destination, here's the source, which is the same as this one. Some source IP, destination IP, and this is what we call the IP packet, this whole thing here. Remember, it will be encapsulated with the Ethernet header, which the Ethernet header will consist of the destination MAC address, source MAC address, and a trailer. And the trailer usually is the frame check sequence. All right, so that's about unicast. Then we'll have the broadcast. Remember, for the broadcast address in the network, we had 255 in IP addressing, and here we will have FF, which is all ones. So an Ethernet broadcast frame is received and processed by every device on the network. It has a destination of all Fs. And as you remember, we have 12 Fs. So that's 2, 2, 2. There you go. If you count them, that's going to be 12 Fs or 12 hexadecimal digits of value F. And the frame sequence will look like this. So this is my destination. The source is the same. Source IP, destination IP, user data, that's the IP packet, nothing to worry about. And here we'll have the frame check sequence. And in that case, the message will be sent to all devices in the local area network. And then we'll have the multicast. Multicast from one to many. One to many, but not all. All will be the broadcast. So an Ethernet multicast frame is received and processed by a group of devices to the Ethernet that belong to the same multicast domain or group. So there is a reserved address for this. So the first 3 bytes or the first 6 hexadecimal digits should be 01005E. So there is a destination MAC address. So these are the first 3 bytes. When they encapsulated that on IP version 4. Let's not worry about IP version 6. So for IP version 4, memorize this address. It's 01005E. So here, these are the first part here, the first 3, and then there will be like an identifier to the subgroup 0000C8. So here is the source address. There you go. It's the same here. This is the destination address, indicating this is a multicast. Then just few set of computers will take, or few set of destinations will receive the message, and the others will not get the message. All right, so we have the 3 transmission modes. Directly one, or unicast, broadcast, and multicast. Okay, so some fundamentals on Ethernet switching. You notice here that the Ethernet encapsulation is unaware of all these details. It will look at it as a black box. It doesn't know what the data is. It has nothing to do with the IP addresses. So it is completely unaware of the data protocol being carried in the data portion of the frame, such as whether it was IP4 version 4 packet, whether it was address resolution protocol, and whatever. So it's unaware. It's kind of generic, it works for all. So the switch makes its forwarding decision based only on the MAC address. So yeah, like when the Ethernet receives a packet from the internet layer or the network layer, this whole thing will appear as a single package. It is unaware of these details. So the transmission for other hosts will solely depend on the MAC address, destination MAC address. All right, so that leads to a concept of MAC address table. So in each Ethernet switch, there will be a table, pretty much like this. That table expands over the time, and we'll see what will happen. So there's something called a switch learning. A switch learning, basically, when the Ethernet receives a packet, it will check the destination MAC address. If it's not listed, it will add it to the MAC address table. So the switch will dynamically build their table by examining the source address received on the port. So for example, here, PCA will want to send a message. Then the switch adds the port number and MAC address of PCA to the MAC address table. As simple as that. So that's the learning. It received a message from a device that is not recognized. It will add it to their database. Then switch forwarding. It will check the destination address. So if the destination MAC address is a unicast, the switch will look for the match between the destination to that entry in the table. If the destination is there, it will just forward it, as simple as that. But if the destination address is not in the table, the switch will forward the frame out to all ports except the incoming port. So that's the case here. So initially we had the table empty, like in this case. This is an empty table. So host A sends a message to the Ethernet, then the table will be updated. So the table is still quite small. It has only one entry. All right, so it will check the destination. The destination is not within the list. What will the Ethernet do? The Ethernet forwarding, it will send a message to all other hosts connected to this one, and each host will reply with its own MAC address. So the table will build up. So the destination MAC address is not in the table, then the switch forwards the frame out to all other ports, waiting for a reply for each host MAC address. Now then there will be the filtering. As the switch receives frames from different devices, it is able to populate its MAC address table by examining the source MAC address of every frame. So when the MAC address table of the switch contains the destination MAC address, it is able to filter the frame and forward it to a single entry. So for example, if this guy wants to send a message from 1 to 4, like this, it has to go through the Ethernet. Ethernet will check if the destination is within the address table. If it's not, it will send a message to all. Once they all reply with their MAC addresses, the switch will only pick the one with the right destination MAC address and then forward the message to it. So the table here only populated with the destination MAC address. And this is how it goes. So we have, like, these are kind of the steps. There's a switch learning, switch forwarding, and switch, filtering frames. Okay, so forwarding happens in 2 ways. First is store and forward switching. So basically the frame forwarding method will receive the entire frame and computes the CRC. So CRC is something called cyclic redundancy check. It's a method, it's a mathematical formula, which will be based on the number of bits or the number of ones in the frame. So just to check if the message is corrupted or not. So CRC is for error detection. Only. So if the CRC is valid, if there are no error, then the switch will look up the destination and forward the message there. So in order to do that, there will be something called storing. So to do the CRC, the whole message must be stored in the switch. Do the CRC, then forward, in case if there are no errors, forward the message to the destination. Now there is another method which is cut through switching that does not involve error checking. It just whatever you receive, you just forward. So this frame forwarding method forwards the frame before it's entirely received. At the minimum, the destination address of the frame must be read before the frame can be forwarded. So for example, this one, you receive this long frame. So there is the destination MAC address, source MAC address, and there is the IP packet. So this is IP packet. And here we have the frame check sequence. So here is the destination MAC, and here is the source MAC. So in this cut-through switch, it first examine this one and start forwarding to the destination. It doesn't wait for the whole message to be stored. While the other one store forward message, the Ethernet will store the whole thing before forwarding it to the destination. So if you talk about advantages and disadvantages, this one is more robust. Robust in the sense there will be some error detection. And this one here is going to be faster. Why? Because you do not do any checking. You just, whatever you receive, you just forward. So it's not robust. There is an issue there that it's not reliable. You might receive error messages or error packets. Okay, so here a quick concept probably we already know about duplex systems. So we have 2 modes, full duplex and half duplex. Full duplex means you can send and receive at the same time. And both ends of connection can send and receive simultaneously at the same time. While half duplex, you can send, you can receive, but if you are sending, you have to wait. If you are receiving, you still have to wait. So it doesn't happen at the same time. So you can do it only once. So one end of the connection can send at a time. So that's the main difference between full duplex and half duplex. All right. So yeah, that's just like the example of duplexing system. There is a concept here, auto MDIX, and actually this is the last slide for this one. If you guys remember, when we said connect a router to a router and we use a cable, we said, okay, similar devices, we need a crossover cable. While if you connect a router to a PC, we said since there are different devices, then I will use a straight through cable. This was part of the physical layer chapter. So similar devices you need crossover, different devices you need straight through table. And you notice here by the changing the device, the media will change. So connection between devices was required the use of either a crossover or straight through cables. Now the type of cable required depends on the type of interconnecting devices. If they are similar, we need crossover. If they are the same, different, we'll use straight through. However, now technology has been advanced. So nowadays we have switch devices that it doesn't matter what cable you use, it still will work fine. So most switch devices now support the automatic medium dependent interface crossover. So it doesn't matter whether they are the same or different. So when enabled, the switch automatically detects the type of cable attached to the port and configures the interface accordingly. So this one is kind of smarter. Like in here, we have two switches, they are the same, so it's crossover. Router and a switch straight through, they are different devices. Switch and a computer straight through. Router and a PC is a crossover cable, which I think this is incorrect. So this one is also straight through. But it doesn't matter with the auto MDIX, things will happen automatically, configuration will happen by itself. And that's it for the Ethernet chapter. Any questions on this one? Anything on the Ethernet? All right, so we'll go to the other topic, data link layer. Okay, let me share my screen again. So this one, there will be a lot of slides. That's something we already have been seeing before when it comes to topologies. So data link layer, as we have seen, is below network over the physical. It has two sublayers, LLC and MAC. LLC, logical link connection, and there's the media access control. So the job of the data link layer is network interface card to network interface card communication. All right, so here are some features or jobs of the data link layer. It enables upper layers to access the media. By upper layers, we mean network and above. Now the upper layers are unaware of the type of media, whether it was wired or wireless, copper, fiber optic. It accepts data usually from layer 3, whether they are IP version 4 or 6, and encapsulates them into layer 2 frames. Layer 2 frames, we have seen them, they are the Ethernet frames. Now controls how data is placed and received on the media. So basically we have the data. We have source IP, destination IP. Then we will have source MAC, destination MAC, and we have the frame check sequence. So this whole thing is the frame packet of Ethernet frame packet. So this one, how the data is placed in the media, exchange frames between endpoints over the network. It receives encapsulated data, usually layer 3 packets, and directs them to the proper upper layer protocol. We have done that actually probably in week 2 or 4, how communication happens between one side to the other. Also, it does error detection through the CRC or the frame check sequence and rejects any corrupted frames. This is exactly from the previous slide. LLC, logical link control. It's a software. It's a sublayer in the data link layer. It just manages the communication between upper layers and the physical layer. The media access control, it does the encapsulation for the IP packet before sending it to the media. It's more related to the hardware, and we have seen that there are different protocols for each hardware device or each media device. We have seen this LLC 802.2, Ethernet 802.3. Let's not worry about wireless LAN and wireless PAN. And for the Ethernet, we have seen there are sub-technologies depending on the speed of the network. All right, so what is the job of the LLC? It takes the network protocol, which is typically on like whether IP version 4 or 6, and adds layer 2 control information to help deliver the packet to destination node. Then the MAC sublayer will do the encapsulation and other hardware that's responsible for sending and receiving data over the network. So the MAC sublayer will do this job by frame delimiting, addressing, and error detection. So delimiting means that the framing process provides important delimiters to identify fields within the frame. These delimiting bits provide synchronization between transmitting and receiving nodes. Yeah, synchronization here, like you're sending data in a sequence. So frame number 1, frame number 2, and so on. And those could be also part of the trailer that is added to the IP packet or data packet. Addressing, it provides the source and destination MAC addresses. So provides source and destination for transport the layer frame between devices in the same shared medium. Now the error detection, that's the trailer, is the frame check sequence, which is also cyclic redundancy check to detect if there are errors in the message. All right, topologies, we have seen that a lot, so I'm going to go over it real quick. Physical topology, basically, it tells you the real physical location of the device and their, let's say, the shape of the network, while the logical one, it's more about IP addresses and stuff. So this is the physical topology that, okay, you say this is the server room, it's room 215B. The web server is in rack 2 and shelf 1. The email service is rack 2, shelf 2, and so on. The switch here is in rack 1, shelf 2, and the classes, and so on. So here we are talking about physical features where the devices are actually. Now, in the logical topology, you are not worried about the physical location as long as you have the IP standards. IP addresses here, the switches, and so on. And there is now, add to the previous one, there is a wide area network topologies, which is basically routers. They are kind of commonly interconnected using 3 common physical topologies. Point to point, like in this one, just 2 LANs next to each other. Remember, each router usually represents a LAN. Hub and spoke, like this one, this is a hub that distributes the message to all, so hub and spoke, and there's like a mesh. Mesh, everything is connected to each other. So LAN topology is pretty much like the previous one. There's a star topology, there's extended star topology, ring topology, and bus topology. So that's something we already know on when we covered like the first weeks of the course about topologies. So let's focus now a little bit on bus topology. We're going to talk about it when it comes to some technologies. Yeah, think of this chapter like it's kind of revision to a lot of concepts. We just talked about half duplex and full duplex. So in half duplex, yeah, if this one sends, this one just receives. It's kind of simple. But with full duplex, they can send and receive at the same time. It doesn't matter. All right. So there is access control methods. Ethernet LANs and wireless LANs are example of multi-access network, means that you can access, disconnect, access, and disconnect. So you can have as many access points or access instances as you want. So a multi-access network is a network that can have 2 or more end devices attempting to access the network simultaneously. So in that case, how will the network behave? So 2 devices want to connect to the network at the same time. So there are 2 basic strategies for shared media, pretty much like the Wi-Fi. There is contention-based access and controlled access. So let's talk about contention-based access, which is kind of very simple. And it's mainly 2 technologies here, whether you are using wired and whether you are using wireless. So in contention-based multi-access network, all nodes, they are in half duplex mode and they are competing, and that's what they call it, contention. So it's like contenders. There are people competing or hosts competing to use the medium. However, only one device can send at a time. So pretty much like this. So this device, once it's in the frame, that's it. So this guy won the challenge, and he's the one who can send data. So we'll have two technologies here in this case. So there is carrier sense multiple access with collagen detection, CSMA, CD. And this is just for bus topology, Ethernet LANs. So this one is bus. Keep that in mind. I'm going to ask you a question on that one in the final. Bus topology, Ethernet LANs, they use CSMA, CD, collagen detection. The other one is kind of similar, but collagen avoidance, and that's strictly for wireless LANs. So carrier sense multiple access with collagen avoidance used in wireless LANs. And let's see the difference between each one of them. For contention-based access, the one with the collagen detection, so this computer sends a message. The medium is available, so I will send a message to PC3. Here is PC3. So it sends a message here, go to the switch. Now the switch will check the message. All right, so let's assume that PC2 wants to send the message, but then what? The media is already occupied, so it will wait. So there is a detection happen. To avoid the detection, the PC2 will wait until transmission is finished. So here PC2, I have a frame to send, but I have to wait because I'm receiving a frame. So both PCs will receive the message, but then PC2 realize that, okay, this message is not meant for me, so I'll discard it. PC3 will take the message because it is the actual destination for that message. So that is for collagen detection, and that's mainly for bus topology. Now for wireless LANs, it's a bit different, but there is a lot of similarity. However, here you are strictly using wireless. It has some additional technique. Now in wireless environments, it may not be possible for device to detect a collision because it's not a guided media. Like in this one here, okay, the message has been forwarded. So this guy knows that this media is occupied. And that's what we call a guided media, but wireless is unguided media. So there is no possibility to detect a collision. However, when you use avoidance, it does not detect collisions, but attempt to avoid them by giving a waiting time. Now, waiting time means that if a device wants to send a message, it will send a message along with a waiting time or some time period or a counter. So each device that transmits data includes the time duration that needs to the transmission. So for example, host A wants to send a message to host C. So the message will go through the router, the wireless router. So that's wireless. And along with the data, there will be duration, like 2 minutes. Now this router will direct the message to wireless to C. Now B will not receive the message, but it will know that this router has been occupied for 2 minutes. So it will wait. So each device that transmits includes the time duration that needs to be transmission. All other wireless devices receive this information. So the timing information here will be received that there are 2 minutes waiting time and know how long the medium will be unavailable. So here's, for example, I see in the wireless frame that the channel is unavailable for a specific amount of time, so I cannot send. I see in the wireless frame that the channel is going to be unavailable for a specific amount of time, so I cannot send. I'm receiving this wireless frame and saying that wait for 2 minutes. So that is contention-based access with collision avoidance. The previous one, the channel, there is knowledge about it. And you can detect collisions, and here you can avoid them. Now, controlled access, basically when you share the medium, it's kind of like taking turns. So in controlled-based multi-access network, each node has its own time to use the medium. So each node must wait its turn to access the network. So yeah, pretty much like sharing the medium, each one has its own turn. All right, almost done. Datalink frame, the datalink layer prepares the encapsulated data, usually in whether it was IP version 4 or 6 packet for transport across the local media by encapsulating it with header and trailer to create a frame. We have seen the contents of the frame, so let me write it real quick. In here, destination MAC, and in here, source MAC, destination IP, source IP, and in here we have the data, and in here we will have some trailer, which is basically the frame check sequence. This is what we called the IP packet, and this whole thing is the Ethernet frame. So the data link protocol is responsible for card-to-card communication within the same network. Each data link layer frames has 3 basic parts: header, data, trailer. So yeah, we have the header here. Here is the whole set of data, and here's the trailer. And there you go. So frame start and stop indicator flags. So at the header with the trailer, so there you go. We have frame start and frame stop. So this information detects the beginning and the end of each packet or each frame. Used to identify the beginning and the end of the frame. Addressing indicates the source and destination nodes on the media. Type, identify the layer 3 protocol and the data fields. So this one addressing is the MAC addressing. And here is more into IP addressing. So control, identify special flow control services such as the quality of service, which is not always there. We did not see it. Data, this is the actual data you have, contains the frame payload, packet header, segment header, and the data. So this is the actual thing. This is the actual data. Now the trailer is responsible for error detection, the frame check sequence, included after the data for the trailer. So in the exam, don't be surprised that you have to draw something like this, but not this one. Something like, okay, not in this slides. Okay, I'll go back to this one, then I'll go tell you which one you need to memorize. Oh yeah, in fact, this is the last slide. So in the Ethernet, don't be surprised that you're expected to know something like this. So draw, or I'll give you the table, and you have to fill each field. So this is the destination MAC address, source MAC address, source IP address, destination IP address, user data, and trailer.